Hello, friends. On June 4, 1996, the Ariane 5 rocket lifted off from French Guiana and exploded just 37 seconds later. The cause was a single software bug. A 64-bit floating point number was converted into a 16-bit integer, and the value was too large to fit. The result was a crash that destroyed a rocket worth roughly $500 million. No hardware failure, no design flaw in the physical structure, just unverified software running on a critical system. And here is the uncomfortable truth. This kind of failure happens more than you might think. In this video, we are going to explore how software verification works, what tools engineers use, and how teams decide how much proof is enough. Let's start from the beginning. So what exactly is software verification? At its core, verification is the process of confirming that a software system behaves according to its specification. A specification is a precise description of what the software is supposed to do, the rules, the constraints, the expected outputs for given inputs. Verification asks one focused question: does the system we built actually match that specification? It is not asking whether the specification was a good idea. It is not asking whether users will be happy. It is only asking whether the code faithfully does what it was designed to do. This makes verification a technical, measurable activity. You have a written contract for the software, and you are checking whether the software honors it. This distinction will become very important in the next slide, where we separate verification from a closely related idea called validation. There is a classic distinction in software engineering that trips people up all the time: verification versus validation. Verification asks, did we build the system right? Meaning, does the code match its specification? Validation asks, did we build the right system? Meaning, does the specification itself reflect what the user actually needs? Think of it this way. You could perfectly verify a bridge control system. Every line of code matches the spec exactly, and still fail validation if the spec told you to open the bridge at the wrong times. The code is correct. The requirement was wrong. Both matter enormously, but they are answered with different methods. Verification uses technical tools like testing, static analysis, and formal proof. Validation relies more on user research, requirements review, and acceptance testing. For the rest of this video, we will focus on verification, the technical side of proving code does what it claims. The most common form of verification is testing, and specifically dynamic verification, because the code actually runs. Think of it in 3 layers. Unit tests check individual functions in isolation. You give a function specific inputs and assert that the outputs match what you expect. Integration tests check that separate components work correctly together. System tests exercise the full application end-to-end, simulating real-world scenarios. Testing is powerful, practical, and accessible. It catches real bugs and gives teams fast feedback. But it has a fundamental limitation that Edsger Dijkstra captured perfectly. Testing can show the presence of bugs, but it can never prove their absence. No matter how many test cases you write, you cannot cover every possible input combination for most programs. Testing is essential, but by itself it cannot give you a guarantee of correctness. That is why engineers developed the next category of tools. Static analysis takes a completely different approach. It inspects your source code without ever running it. Tools like Klang's Analyzer, ESLint for JavaScript, or Coverity read through the code, build internal models of how data flows and how types are used, and flag problems before a single instruction executes. They catch things like null pointer dereferences, where code tries to use a pointer that holds no address. They catch type mismatches, where a value of one type is incorrectly used as another. They flag unreachable code that can never execute, which often signals a logic error. Because static analysis operates at the level of the source code itself, it can examine all possible paths through a program, not just the ones your test cases happen to trigger. It is fast, automated, and integrates cleanly into a build pipeline. But static tools can produce false positives, and complex behaviors at runtime may still slip through. When the cost of failure is catastrophic, think flight control systems, medical devices, or cryptographic protocols, engineers turn to formal methods. These are mathematical techniques that can actually prove correctness, not just observe it in tests. The 2 main approaches are model checking and theorem proving. Model checking works by building a finite mathematical model of the system and then automatically exhausting every possible state to verify that a given property always holds. Tools like Spin and TLA+ are used in industry for this. Theorem proving goes further. You write your program's behavior as a formal mathematical statement and then construct a logical proof that the statement is true. Tools like Coke and Isabelle assist with this. Formal methods require significant expertise and time, but for systems where a single bug can cost lives or millions of dollars, that investment is justified. They offer something testing simply cannot: a guarantee. All right, let's bring it all together. Software verification is the discipline of confirming that code matches its specification, and you have a whole spectrum of tools to do that. On one end, testing is fast and practical, but it cannot cover every case. Static analysis broadens your coverage without running the code, catching whole classes of errors automatically. Formal methods sit at the far end, expensive and demanding, but capable of mathematical guarantees that nothing else can provide. The key takeaway is this: the right approach depends on the risk involved and the cost your team can absorb. A startup building a note-taking app and a team building an aircraft autopilot face very different stakes, and they should invest in verification accordingly. Most real-world systems use a combination of all three layers. Thanks for watching. If this helped you think more clearly about correctness and proof, you are already thinking like a software engineer.